Hi guys, in this video we will look at some of the general information related to the reaction mechanisms and reactivity of acid derivatives. Now the primary mechanism that we'll be looking at here is called nucleophilic acyl substitution. It is thus another NAS. But usually when you hear NAS, it refers to the nucleophilic aromatic substitution mechanism we saw when we were looking at aromatic chemistry. Now I can also add that the two NAS mechanisms are actually pretty similar in many aspects. We will maybe point that out a little bit later. Now the nucleophilic acyl substitution only applies to the acid derivatives that contain a carbonyl. It does not really apply to cyano groups. Okay, so it's really a carbonyl mechanism, but it's a carbonyl that contains ultimately a leaving group. And here X is your leaving group. All right, and we showed this on the cover sheet here. Instead of X, I actually showed Lg. So carbonyl with a leaving group. Typically we react this with some type of nucleophile and we can replace the leaving group with a nucleophile, so it looks like a substitution. But this is not SN1 or SN2 because you do not do these mechanisms on when the leaving group is on an sp2 carbon. And we said the same thing when we were looking at nucleophilic aromatic substitution. This is instead an addition-elimination mechanism. Now your mechanism involves the nucleophile. This is very generic. Let's have a lone pair here. Typically a nucleophile will, yeah. Electrons add to carbonyl. Okay, we do not break away the sigma bond. Instead, we break away the pi bond from this carbon. It's the weaker bond. And so electrons, bonding electrons, move on to oxygen to become the third lone pair. Oxygen becomes negative. Nucleophile is now bonded to the carbonyl carbon, the original carbonyl carbon. This would be a nucleophilic addition. Typically, this is your rate determining step for this entire substitution mechanism. Because we are forming a higher energy anion here. We can call this a tetrahedral intermediate because the carbon is now tetrahedral, where originally it was sp2 trigonal planar. Okay, why would the nucleophile add to that carbon? Well, that carbon is partial positive because we have dipole, oxygen pooling. We also have the X group pooling because the leaving group is typically going to be electronegative as well, such as a halogen or even another oxygen or nitrogen. But certainly we have the carbonyl oxygen pooling creating a partial positive on the carbon, which is why the nucleophile would be prone to attacking there or be attracted to that carbon. Okay, we can get the magic of bond formation. All right, from the tetrahedral intermediate, electrons will then come back down and kick off the leaving group. All right. Now we could, let's add something. We could go back. These electrons could come in and kick off the nucleophile. Sometimes. Okay? Is it possible? We'll talk about that going forward. Here, though, we're going to be looking to kick off the current group, because if we kick off the nucleophile, we don't get anything new. We go back to the starting materials. We're not going to kick off a plain carbon, okay? But instead we can kick off something maybe like a chlorine if the original was an acid chloride. We've also said this several times, and we'll say it again. Anytime you can make a double bond, a pi bond, by kicking off a leaving group, that's typically an easy thing to do. It's going to be fast and easy. And so we can do this, and we can call this elimination because the X group has been eliminated. Now, I'm not showing any charge here because it's very generic. So we have an addition elimination to give overall, the nucleophile has replaced the X group, overall substitution. And the carbonyl is reformed here as we expel what is to be the leaving group. If we do a reaction coordinate diagram for this two-step mechanism, we can show formation of B, the tetrahedral intermediate, okay, A, B, and C. And then a fast step to form the product. I'm not going to distinguish the energy between starting and product, but very often your reaction is going to be exothermic. Okay, what about leaving group requirements? What's the best leaving group? Well, since the leaving group, since X leaves in the fast step, the easy step, leaving group ability is not as critical as in an SN1 or SN2 reaction, where the leaving group leaves in the slow rate determining step, right? Typical leaving group for SN1, SN2 is your halogens, tosylate, with iodine being the best of the halogens. Here, the leaving group X can be any atom or group that can handle a negative charge. If you've ever seen the atom be negative, it can leave in this mechanism. This includes halogen, oxygen, nitrogen, sulfur, and even carbon sometimes. But if the carbon is stabilized somehow, it's not going to be a plain carbon. We'll see that example when we look at the haloform reaction during test 4. All right, a standard carbon such as a methyl, ethyl, butyl, etc., or hydrogen will not be a leaving group in this mechanism. But many other groups will be, again, because the leaving group leaves in the fast and easy step. Okay. Now, this is an overview. We will refer to this, okay, once we start doing specific reactions. There could be other things to say at this point, but I'm going to let those things sort of come up as and discuss as we need to. Next topic, reactivity of the acid derivatives. All right. This was also shown in the diagram, of course, as we mentioned several times already. The acid chloride is the most reactive, then anhydride, then ester, then amide. All right. And that's the same thing I say here. I'm not going to rank the cyano group, the nitrile, but it's relatively unreactive. It would be ranked similar to an amide. So why this ranking? All right. Well, ultimately, the carbonyl is more electrophilic, all right? That is, there's more partial positive on the carbonyl when we have a strong electron withdrawing group attached. It's going to be less electrophilic when we have an electron donating group attached. Now, all of these have a carbonyl. So we cannot just look at the carbonyl. That does make the carbon electrophilic. But what does the other group do? Okay, what does the X group do? That's what we really need to look at to see the difference. Now with an acid chloride, or so-called acyl chloride, the X group is chlorine, all right? And because the chlorine is fairly electronegative, and so we got a strong dipole in this direction as well, we have two atoms withdrawing, making this substantially partial positive, or we can say very electron poor, and thus is going to be reactive as an electrophile. Okay, let's say highly reactive because we can compare it to others. Compared to the others, it's more or highly reactive. Now, acid chlorides are so reactive that they will react with water, and because of that, you don't typically see them in nature where there happens to be water. Acid chlorides tend to be reactive intermediates that you use in the lab for synthesis. They're not going to be an end product. You're never going to see an acid chloride as a drug. They're just too reactive. Things that are highly reactive are going to react with water, or in some cases, if they're highly redox active, they'll react with oxygen in the air. Okay. So high reactivity can equate to sort of unstable. All right, things like that. We'll talk about it more. Next is an anhydride. We'll cover anhydride specifically. It is where you have two carbonyls and oxygen bonded to two carbonyls. Now when you react them, and as we'll say later, this is going to be the leaving group, okay, or X group. You attack one carbonyl and all the rest is your leaving group. Okay, same thing here. You can attack this, X can leave. All right, the oxygen and the other carbonyl, all that would be your leaving group from this carbonyl. If it's symmetrical, you could attack this one and then all of that would be the leaving group from that carbonyl. But let's consider here, we're attacking this carbonyl, all right? This is your leaving group. But if we consider resonance, this oxygen is conjugated with this carbonyl, but also the one to the right. And if we consider the conjugation to the carbonyl on the right, we can draw this resonance structure where these electrons move here and these move up. And we see that this central oxygen has some partial positive charge due to the contribution of this resonance structure. And so it is an electron withdrawing group. Okay, it's going to be electron greedy. It's going to pull electron density so it can go back towards neutral. All right. But it turns out it's not as strong as a withdrawing group as the chlorine. All right, and because it's not as strong as a withdrawing group, this carbonyl is not going to be as electrophilic as the acid chloride, and thus the anhydride is not as reactive as the acid chloride. Now, if we can then consider next esters, we also have the oxygen. But this oxygen is not conjugated with a carbonyl over here. That's going to be a plain carbon group. So we can't make the same argument of these electrons being pushed or pulled to the right. Instead, those electrons are only conjugated this way. And if we show resonance structure this way, we actually see electrons moving into the carbonyl. All right. And that's not going to make this carbonyl carbon more electrophilic. It'll actually decrease the electrophilic nature. And so actually the oxygen here is more electron donating here. Certainly than it is in the anhydride. And so esters are less reactive at the carbonyl than anhydrides. Okay, last on the list is amides. Here, the nitrogen is a stronger donator than the oxygen. Okay, it donates strongly into the carbonyl. To give this here, the reason nitrogen donates more than the oxygen is because nitrogen is more willing to become positive compared to oxygen. Oxygen is more electronegative. Periodic trend. So it likes to hold on to its electrons more. It's going to be less willing to do this resonance than nitrogen. Nitrogen donates by resonance more than a comparable oxygen. All right, so we have a strong donation into the carbonyl by the nitrogen. That's on the other end. Compared to the chlorine, its net effect is strong withdrawing. Okay, yes, it can donate by resonance, but with halogens typically they withdraw strongly inductively, but the nitrogen donates strongly by induction. All right. This is actually a significant contributor, okay, for amides. All right, high electron density on the oxygen. We will refer to that later. But I can actually give you some NMR evidence for this. If you look at DMF, okay, which is a common solvent, you've actually used it in the fluorine lab project. All right. We can show resonance structure, okay. And this structure is a significant contributor to the actual structure, and because of this the two methyl groups are not equivalent. Okay, here you would expect the two methyl groups to be equivalent if we consider free rotation around this single bond, but actually there is a significant amount of double bond character between the nitrogen and carbon. And the double bond character is going to restrict the rotation around the nitrogen-carbon bond, and that makes these two methyls not equivalent because one is cis to the oxygen and one is trans. All right, so are they equivalent or not? Well, we can actually look at the NMR of DMF, and if you do that, you will find that the methyls give different signals. They are not equivalent. They both are singlets, but it's two different singlets. Here's the H. It's kind of like an aldehyde, but it's not really. It's really the H of an amide, but it's similar to an aldehyde, going to be downfield. It's also a singlet. It's also water here. Okay, real NMRs typically always contain water. All right, DMF is a very polar solvent. It probably has moisture in it. You also have moisture in the atmosphere. All right. but the methyls are not equivalent. That's because of the resonance contribution of this lone pair. And if you look at the resonance hybrid, again, there is double bond character between the nitrogen and carbon. This is actually good evidence for resonance. All right. Next, let's look at interconversion of acid derivatives. What can we say about that? Well, you can only convert to a less reactive derivative. All right. Well, acid chlorides can be converted to anhydrides, esters, or amides because they're all less reactive than the acid chloride. But an ester, on the other hand, can only be converted directly to an amide. You cannot convert an ester directly to an acid chloride. All right. Now I'm talking directly. We can convert any to another one indirectly if we go back to the carboxylic acid. Now this is shown here. The acid chloride can be converted to the anhydride, ester, or amide. An amide cannot be converted back to, for example, an ester. Not directly. But you can convert the amide to the acid. Okay? Then, from the acid, you can go to the ester. All right? But that would be an indirect route to the ester. We're talking direct here. So you cannot convert an amide to an acid chloride by reacting it with chloride anion. So why can't you do this? First off, reactivity scale. An amide is the least reactive carbonyl. You would have to use Cl-, okay, as the nucleophile. Well, it's a pretty poor nucleophile. All right. It can act as a nucleophile, but your halides are not great nucleophiles. Iodide would be better. All right. So getting this here to take place, you just have low reactivity. Now, even if the chloride did add to the carbonyl and you got to this tetrahedral intermediate, when the electrons came back down to reform the carbonyl pi bond, which would you kick off, the Cl or the nitrogen? Well, the Cl is a better leaving group. So, and indeed, it's the one that would get kicked off and you would come back to the amide. And thus, you will not make I'm actually going this way. If you keep going, you'll go back to the amide. You're not going to be able to kick off the nitrogen and have an acid chloride. Now compare that to below. If we react an acid chloride with an amine, such as ammonia, we have a very reactive carbonyl, lots of partial positive. We have a good nucleophile, amines, and an organic one. We call them strong nucleophiles. We can get to a tetrahedral intermediate. I see that my H is gone. Okay. I have already taken care of proton. We got to talk about that. We don't just lose protons. All right. When do we take care of protons? It looks like I already did that. All right. Then electrons back down, and we can kick off the better leaving group. That would give us the amide. This handout is a little bit older. I have become more strict on making sure we have lone pairs on charged atoms. I kind of skipped a step. By the way, when you get to biochem, you're going to lose protons all the time. You got to know what's going on. That's what I call taking care of the proton. All right. Circling lone pair when we do mechanism, yeah. Okay. I've become more particular about this because I think it's helpful for you. All right. So, hopefully this looks like a reaction that should proceed to give a new product, where up here you got some difficulties. And indeed it will not give a new product. Okay, let's also talk about a general concept. Important. Protonation of the carbonyl makes it more reactive as an electrophile. When we first looked at adding to a carbonyl, we said, well, the oxygen's pooling. Okay, it's going to be partial plus because of that. We also have the X group sometimes pooling. All right, and that may make it even more partial positive. But we can add to that. By protonating the carbonyl. First off, an example. If you take an ester and try to react it with pure water to maybe replace the O-methyl with an OH, there will be no reaction. But if you include an H plus catalyst, okay, and if you show these combined, it's H3O plus, right? We can get a reaction. So the difference is we're reacting it with water in both cases, but we only get a reaction if we include a strong acid catalyst. Why? That's because the very first step you want to show here in your mechanism is protonation of the carbonyl with the strong acid. It's just an acid-base reaction. Lone pair attacks H. We have oxygen is now bonded to H. We call that protonation of the carbonyl oxygen. That makes the oxygen positive. And the positive oxygen is going to be even more electron withdrawing. Okay, we've made it mad. It's like, I need my electrons back. Sorry, carbon. I'm going to take this weakly held pi bond and pull it towards me a good bit more than I normally would. In fact, we can do that and just show resonance. If we move the pi electrons onto oxygen, we can show this resonance structure, and we see that the carbon there has a good amount of partial positive character. Because of that, the water will now add to the carbonyl carbon. All right, and when you do that, you can always work with any resonance structure. Here I'm adding to this, or we could add just right here. Either one of these reactions would give this. You can always work with any resonance structure. Neither one is actually real, right? The true structure is actually the resonance hybrid. We typically do work from this one. This is the one we'll show. Okay? But you need to understand the resonance here and the positive charge on the carbon here in this resonance structure. Overall, it's a partial positive on that carbon. And we can do our nucleophilic addition. All right. Now, if you do not have the carbonyl protonated, it turns out that while that is still partial positive, it is just not as partial positive as when the oxygen is protonated. And so it turns out that these electrons just will not come in here. Okay, much diminished reactivity, and typically it just doesn't react. Protonation of the carbonyl allows it to react, and that's why the H plus is ultimately your catalyst. All right, protonation of the carbonyl. All right, with what? With strong acid catalyst. Water is not an acid. We're not going to protonate the carbonyl with water. All right, carbonyl is only protonated under acidic conditions, not under neutral conditions, and certainly not under basic conditions. All right, I have students all the time protonating carbonyls under basic conditions. No. Requires a strong acid to protonate a carbonyl, because ultimately the carbonyl oxygen is not very basic. It is weakly basic. And when you do protonate the oxygen, it's actually not a good equilibrium. The equilibrium actually looks like this. Okay? You're really only protonating maybe, I'd have to look at the numbers, but maybe 1 out of 1,000,000, okay? But that one that you protonate, the water then attacks. And then once that one is removed from the equilibrium, another one gets protonated. Then it attacks, and then another one gets protonated. And of course all that happens in lightning fast. And in the course of maybe a second, you did that 1 billion times, yeah? Okay, I showed this just with an ester, but this includes or applies to all carbonyl functional groups. Acid derivatives, but also aldehydes and ketones. When we get to test 4, we'll be protonating the carbonyl of aldehydes and ketones as well. All right, so it's a very general concept. Textbooks sort of just talk about this as they're talking about other things. And these general concepts sort of never get the focus that they need. What I'm trying to do here is really focus you in on this general concept. Please work to understand it. Okay, a couple of more applications. You can take a look. It's like an aromatic mechanism, NAS, nucleophilic aromatic substitution, nucleophilic acyl substitution. Take a look. It's a neat mechanism, apparently. Take a look. SN2, okay, it's other chemistry. Usually anything I hand write is something I want you to take a look at, yeah? All right. Again, take a look at these. We've already mentioned this in previous video. Synthesis. Okay, so there's some general information about your acid derivative mechanism, reactivity trends, and the idea of protonating your carbonyl to make it more reactive. We'll end here, guys, and in the next video we'll pick up in the outline that we have. We'll pick up Roman numeral 2, reactions of carboxylic acids.